Okay, so now we're going on to the next problem where we're dealing with a ladder. And this is a ladder just sort of resting up against a wall. So we're told that we have friction on this bottom surface. So I kind of just copied and pasted the free body diagram because I thought it would be a little bit more readable because there's some weird stuff kind of going on there. Um, but okay, so when we're initially given the problem, we're asked for the minimum angle theta required so that the ladder will not slip. So we're asked for the ladder not to slip. So that means that all of the forces on the ladder need to be balanced. So there's no net force in the x direction, right? X, y, or torque that would cause any rotation of the ladder or any downward slip or sideways slip. So it's not going to slip down, it's not going to slip sideways, and it's not going to rotate. So we want to set everything equal to 0. Okay. So we're asked to find this minimum angle. So we're going to model our problem and our minimum angle required between the ground and the ladder. Oh, we're trying to find this theta right here. Okay. So we're going to model everything using that theta and set everything equal to 0. And then we're just going to try to algebraically figure out how we can solve for that theta. Okay. So looking at this, we know we have a couple of things going on. I have a contact point here. I have a contact point here. I have this weight hanging off the ladder. So I would have a force coming down here. But then the ladder itself also has mass. So there would also be another force with the weight of the ladder that would be acting at the center of mass for the ladder. So I'd have one more force coming down for the weight of the ladder. Okay. So let's think about what kind of pivot points I would have. So I have a smooth wall. So smooth is kind of like a keyword for no friction, but it also says there's no friction between the wall and the ladder. So this is just an object resting on a frictionless surface. So because we have an object resting on a frictionless surface, we're going to have no force that's going to resist it moving side to side, right? So it's just that one pinning force. It's just like touching that surface, but there's nothing that's resisting it moving up or down on that wall because that wall has no friction. So it's just that one force there. Okay, down here we have a pivot. And we saw that in the previous problem. If we have a pivot, we're going to have a force that's resisting in this direction. I'm not sure what they call it. Yeah, okay. I'm going to call this Fn1. And then we also have a force that is, wait, is it pivot? Oh, I'm sorry, it's not a pivot. It's just friction on the ground. So frictional force between the floor and the ladder. So it's resting on the ground with the normal force. And then we also have a frictional force. And our frictional force is going to go this way. And it's preventing the ladder from sliding out. So if the ladder, as it's coming down, if it moved away from the wall, it would be moving to the right. And so that frictional force is going to point towards the left because we want to pin it, right? We want to prevent motion. Okay, so if we scroll down, we can see that that's how we have everything modeled for our free body diagram. They just took this weight basically and broke it off and turned it into this hanging weight here. This is the weight of the ladder coming down from the center point. This is the normal force touching the wall, right? And then this is the pinning forces on the bottom, okay? So for this angle theta, if we remember kind of some basic stuff for geometry, if I draw two parallel lines and I consider the floor and this line at the top like two parallel lines, I know that this would also be theta, right, at the top. If I just have one line that's bisecting two parallel lines, I can say that these angles are equal. Okay. Then there's one other thing too. We want to know the weight, the angle that that weight is hanging from, and then the weight of the ladder. So we can use that angle theta, okay? And let's just draw down and say that we have a right angle because when we have something hanging down, and if it's just going straight down, gravity is going to be acting straight down. So we know that we can have like a 90-degree angle with the ground in this case because the ground is just flat, it's not tilted up. So we know that this angle is going to be 90 minus theta. And we also know that this angle would also be 90 minus theta, right? If we come down and draw like another right triangle, these would both have that same angle. So this guy and this guy are both 90 minus theta. Okay, and we're going to use that for when we set up our equations. So we're going to set up sum of forces in the x, sum of forces in the y, and then all of the torques. And then we're going to look at what we have and see how we can do some algebra to find the value for that angle. Okay, so let's start with the easy one that we have the least of, sum of forces in the x direction. Okay, so if we look at our free body diagram, we have this normal force here, and we have this frictional force. So we have Fn1 in the positive direction, and then we are minusing this Ff, because if we just decide that this is our positive x and this is our positive y, those are the signs that we're working with. Okay, we're going to set that equal to 0. Okay, so far so good. All right, next let's look at all of our sum of forces in the y direction. So for sum of forces in the y direction, let's look at everything that's pointing up. Okay, so we have Fn1, so that one's positive. Fn1. And then everything else is negative. All the other ones are pointing down. So we have this force pointing down and this force pointing down. So minus 245 newtons, and then we have minus 98 newtons. And because this is static, so we can set it equal to 0. And we can simplify things kind of nicely. So, all right. So far, just looking at this, I can figure out the value for, I'm sorry, did I say Fn1? This is Fn2. That's the wrong subscript, I'm sorry. Fn2. So I can get my Fn2 value right away, probably from here. So I can say that Fn2 is equal to 343 newtons, just because I don't have any other variables in this equation, so I'm just going to pull it out. But I still don't know my Fn1 or my force of friction. But let's see, I can relate my frictional force here. I can say my frictional force, because it's acting on this surface, so I have to take the normal force on its surface. I can say it's equal to mu Fn2, right? Because this is my normal force on this frictional surface. So I have Fn2 here, and I think the problem also gives me, yep, I have this mu value as well. So I can go ahead and solve for that one, 0.6 times 343 newtons, and I can get my frictional force. I'm just taking these right away just because they're easy, just trying to find the easy values first, 205.8 newtons. Okay, so I solve for this guy. And then I also know my Fn1, right? Because I know that it's going to be equal to the frictional force because I have this equation up here that tells me that. So then I can also say that's also equal to Fn1. Okay, so that makes my life a little bit easier here. Okay, so what about the torques? So that's going to be the harder part for this. So let's see here. Oh, and actually we should say that it's going to be less than or equal to, because this is static friction, it's not moving. It's not really going to be that big of a deal for this problem, but to be technically correct, because our static friction equation for mu s, F of s is less than or equal to mu s times that normal force. Okay, so we would just want to keep it under that value, or else if it goes over that value, then the ladder would slip and move. Okay, so now let's look at sum of torques. Okay, so we've got a lot of stuff going on here. So for our sum of torques, what we want to do is we are going to start looking at the distances for all of these objects, and we're going to choose our rotation point to be this guy right here. Okay, so that's just because we have, normally it's like these two unknown forces, it makes it easier so we can model less forces. So the distances that we're going to have, so we have this distance, right, for the weight. Then we have this other distance here, right, for this second weight. And then we also have the full distance of the ladder. So we have a halfway point. We have a point up where that 25 kilogram weight is acting. So it's going to be, it's 1 meter from the top is what it says. So if the whole ladder is 3 meters long, then this length is 2 meters. So this is 2 meters here for this length, okay? And then for this guy, we have, oh, sorry, wait, it's the middle. This one is 1.5 because this is the middle length, 1.5 meters for the middle. And then this one is going to be 2 meters, right? Because it's 3 minus 1, and this is 1 from the top. Okay, so that weight is acting at 2. Okay, so, and then the final one at the top is acting at 3 meters. So now that we looked at our distances before we started, let's go ahead and sum everything. Okay, so first, let's look at the torque from the we'll start with the weight of the ladder. So we're just kind of starting in the middle, which is a little weird, but okay. So torque from the weight of the ladder. Our weight of the ladder, we have this 90 minus theta angle. So we're going to take negative 98 newtons because if we think about the way that this is going to cause it to rotate, this is our point of rotation and it would go around like this way, right? So this would be clockwise for us. So that's going to be negative. So normally we see it like rotating from this side, but if it's still the whole circle, so it'd be rotating this way. So negative 98 newtons, and then it's going to be, the distance is 1.5 meters because we're in the middle. And then the angle, we have sine of 90 minus theta. So it's sine of this angle right here. So this is the angle between the force and the distance from the pivot point. So that's what that is. And if you kind of notice, this sine of 90 minus theta is actually just going to be like the vertical component of the force that would be pushing at a 90-degree angle. It's like when we break up the forces into x and y, this would be the y component. Doesn't really matter. You don't have to kind of keep that in mind there, but we'll say this is torque for the weight. Okay. All right. Now let's look at the torque from the normal force on the wall. So we're going to look at the torque from this guy here. Okay. So we'll say torque from Fn1. Okay. So our force is, we found it. We have it over there. We found this Fn1. So it's 205.8 newtons for the actual force. So we're using this equation, RF sine of theta, that we've used a few times before. Let's also look at the direction. So this one would be causing it to go, what is cause it to go clockwise? Sine of theta. Oh no, sorry. Okay, so this is where things get a little bit tricky. Because I'm taking the, I want to find the piece that is acting right at a right angle. So whenever I have these vectors at an angle, I'm breaking them up. And so this one is positive. Okay, so this is going to turn to Fn1 times 3 meters times sine. Okay, so this is my theta here. So sine of theta. Sine of this theta angle here. Okay. So this one's positive. Okay, and then for my normal force for the ground, if I'm taking, if I'm accounting for these two here, right, I have this normal force and then this frictional force. When I'm taking my torque at this point, the radius for both of those is going to be 0, so those will both be 0, right? Plus 0, plus 0. And then the last one I have is the torque from the, I got the weight hanging on the ladder. Oh, sorry, this is the weight of the ladder. And then we're also going to have the torque of the weight for the bag. And then that one is going to be 295, and that one's negative, also going down, 245 newtons. And then the distance away is 2 meters. And then the angle is also 90 minus theta. Okay. So negative, negative. Oh, I'm sorry. And this is Fn1. Okay. So, let's see here. So we have a couple of things going on here, but we're going to use one trig identity to simplify things a little bit. We know that sine of 90 degrees minus theta is equal to cosine of theta, okay? So when we put our equation together, we're going to use that to simplify things a little bit. So we're going to try to come up with an expression where we can get theta on one side so that we can use a number basically to solve for our theta value. Note that because we have like sine and cosine in this expression, it'll be really, we want to kind of end up with, we know that tangent of theta is equal to sine of theta over cosine of theta. So if you have both of these in an equation, sine of theta and cosine of theta, and you're trying to find an angle, it helps to try to algebraically move them around so that you could have sine over cosine, and then you can just take the inverse tangent of one side. So just kind of like a trick here. Okay, so let's kind of like clean things up a little bit because this is a little bit messy. So my sum of torques equation, if I kind of like plug half of this into a calculator, and you can check me here, it's going to turn into 147 cosine of theta, right? Because I have this piece right here, sine of 90 minus theta. And then I have plus, let's see, 205.8, okay, times 3 meters. Sorry, I'm not simplifying this one yet, I guess. And then I have sine of theta for this guy. And then this last piece here, so this was torque from the ladder, this was torque from Fn1, and then we also have, and then minus torque from the weight. And then the torque from the weight for the last guy was 490, just simplifying a little bit, and then cosine of theta. And then all of that is equal to 0. Okay, so we can group the cosine terms basically and the sine terms. So let's add the sine and the cosine terms together. So we have 2112.33 newtons cosine of theta is equal to 2050, yeah, 205.8. So I just divided the other one by 3. So 205.8 sine of theta. Okay, so now we can get that sine of theta over cosine of theta that we were talking about. So I can set my, let's see, sine of theta divided by cosine of theta. So I'll have sine of theta over cosine of theta is going to be equal to, just add a page really quickly here. Oops. Add page is going to be equal to 212.33 newtons divided by 205.8 newtons, and that should give me 1.0317. And let's say this is tangent of theta. Okay, so in this case, if we just do inverse tangent of theta, we're going to get an angle. So tan inverse of 1.0317 is going to give me 45.89 degrees about. So this would be my minimum angle. So that's the minimum angle to maintain. So I want a theta, basically that's going to be greater than or equal to 45.89 degrees to prevent this from slipping. So in order to keep these static conditions, the angle that I want, my minimum angle, is 45.89. Okay. I'm going to go ahead and pause this guy.